Okay.
Hi, I'm Ella, and I'm gonna talk about cabin crew scheduling for flights. It's not quite loading. I was tempted to do that, but nah. Okay, the problem. So, according to the paper I read, they sampled Hong Kong, one of the airline there. They spent 21% of operating expenses for cabin crew, and that make up of nearly half of the airline staff. And bad schedules have consequences because passenger get a bit upset. With the rocketing fuel price, they will want to cut costs while keeping every flight covered. So, yeah. It's more complicated. I also read a few survey articles and another paper about like flight crews, so like pilots and co-pilots scheduling, but cabin crew is more complicated because one is they are cross qualified across multiple aircraft types, so like they can serve any plane. The other thing is they are categorized into multiple classes according to skills and experiences. I watched a YouTube video about that, but let's just say senior and junior. Um, Also, because if one flight is delayed or canceled, it might disturb the future scheduling, like let's say appearing from A to B to C back to A. If A to B is canceled, then the flight crews will not be at B on time to make it to the flight B to C. That's blocked, and they may or may not make it to C to A. That's at least disturbed. Um, for the paper and the problem I will solve, I will stick to the assumption that the flight schedule, fleet assignment, so pilot, co-pilot, aircraft routing have been solved upstream. We don't deal with that. And planning horizon is 1 week at least for now. The formulation of original paper, it does have like 3 different models, so I will just go through the set, data, and variable for all 3 models and talk about the constraints and objectives separately. So R are the cabin crew classes, F for all the scheduled flight, B for all the home bases. We actually didn't really use B, at least in their paper, because they kind of enforce arc consistency and each pairing must start and end at crew's home base. So we kind of just ignore the home base. Set of feasible team pairing, individual pairing from available, and individual pairing from extra. Extra means there's no one at the port and they need to fly someone there, basically. For data, we estimate all the costs using time away from base, and that's for team, available, and extra. They have 3 different values. Same for covers. If the team can cover this flight, and same for available or extra, there are data. So if we have enough people, basically. And more data, required number of crews for the flight, total available class of class R. Mu is the penalty cost for substituting. Substituting is like we are out of cabin crew of class 1, so we substitute with class 2. And big M is the penalty cost of flying somewhere else to that base. Okay, variables select if T1 if we select a team, and assign extra and sub for available, and then extra flight attendant and substitute it with a different class, and they just keep track of number of times it happening because we kind of use the cost as a constant, so we don't like kind of differentiate between flights. Whenever it talks to T, it's about a team of flight crew. Whenever it talks to about P, it's about individuals. So the first model is traditional cabin crew pairing. We are just minimizing the total cost times selected teams of sum of all the teams. And each flight F must be covered by at least one selected team that's qualified. that actually covers the flight. That's the constraint. It's pretty simple, but it's not great, because let's say if a aircraft need to wait at a base for ages and the whole crew need to wait with it, or likewise if like the turnaround is super tight, it just refuel and load the new passenger and take off, then crews will have no breaks. It's not great. So the paper used the previous model as like a baseline and proposed this multi-class individual cabin crew pairing problem with availability and controlled crew substitution. I'm not too sure about what controlled they mean, but we will talk about that. But it's treating each individual flight attendant as their own thing and then compute the cost. So we try to assign available crew first, plus if necessary substitution penalty, plus if necessary extra crew costs, and minimize the whole thing. Then it is subject to these constraints. We need at least like the total number of cabin crews must be at least meet the demands, which is some of requirement. It also at least one qualified crew for each class need to assign for every flight. It keeps track of number of times class R is substituted on flight F, because we can't have like more we can't use more flight attendants of each class than there is, even like after using substitute. And crew availability constraints, so the amount assigned is less than or equal to available. And some non-activity trivial constraints. I think I missed one that's also there. That's just the substitute should be, substitute is here, but like the extra should be less than or equal to available. It's not in the paper, but I feel like you need to get extra from a different base, but they do not index by bases, so it's kind of not there, but it should be there. And another version of it that's simplified, which is basically the same thing, removing substitution. So we kind of ban substitute. If we need extra, we just grab extra. And this constraint is just a subset of what you've seen before. Okay, so that's like goes through the formula to give you the background of the problem. The overview of how they solve it is they use dynamic programming to initialize the warm start. So they kind of find a solution. It's not necessarily feasible, but they found a solution. Then use the master problem and pricing. They column generate all the either team or individual flight attendants feasible flights, and then use MIP to solve it. And for large instances, they replace it with genetic algorithm. There was some heuristic involved. I did not understand it, so I will not discuss it. So DPIA, it provides a warm start. It just quickly generates a small set of legal pairs covering every flight. There's no crew availability constraint, so you will get something feasible. But like you can't it covers everything, but you might be out of people at the end. And we solve master problem and pricing problem alternatively until no improving column exists, and then we do LP and we get LP optimality. Once columns are generated, it's fixed, so we don't touch it again. And MIP is solved only over these columns. So as you can see in the data, we kind of use all feasible pairings as data. We don't touch it ever again. Recovers integer pairings from LP solutions because you can't assign half a flight attendant. Global is not guaranteed because you might miss some integer solution when generating. Okay, so after we know the overall like high level thingy and the very nonsense constraints and stuffs, we look at its limitations. Firstly, because restricting to MIP to the last master problem, it's fast, but like I said, you might just miss some integer solution that's never there. And the cost approximation using time away from base is also a problem. The paper kind of planned the short haul and long haul flights separately, just so they use two different constants for the time away from base. But also like you can have short haul and long haul alternatively in one pairing, and they simply do not consider that. Also, deadhead arcs, that's when flight attendants need to travel as passenger to get to somewhere. Then you obviously need to pay them for doing that, and they do not generate value for that. And they kind of just don't consider that, so that's not great. Also, when they said control substitution, the paper also said all classes can be substituted any other class in either direction. Then what's the point of having class in the first place? So we should probably fix that. And also, if possible, I want to look into flight delay and cancellations and have a new plan, like online plan, but that's like more advanced. So we go to extension and plans of attack. Firstly, I want to compute costs for flight hours, layover, and deadhead. And they will still be approximation because like each flight attendants get paid differently, but also like I just can have a unit price for them. That would be better than just be like cost away from base or whatever. Also, we actually restricting the substitution, so only senior crew can substitute general cabin mate, but not the other way around. Also, if possible, update the schedules upon flight delay and cancellation. In terms of plan of attack, it's a dump of buzzwords because I don't know half of the things I'm gonna talk. Firstly, I'll try to replicate the second model because that's the most complicated or like their main one. And I wanted to do some constraint programming because if you only treat one base, it's like a pool of flight attendants. When they go out, they become unavailable, and when they come back, they go back to the same pool. And we saw like 2 weeks ago, it's kind of nice to use constraint programming. Yesterday, Michael advertised me domain independent dynamic programming. We will learn it in 2 weeks. I don't know what that is yet. So buzzword 1. When yapping outside, I was advertised DISA algo saying it's good for like partial updates in real time, which is kind of good for flight cancellation or like delay. It's like dynamic A start, only looking at the section that got disturbed. And again, I don't know in detail what that is. So data collection. Usually you will contact the author or look up online, but there's a section that it's confidential, so I guess we're done here. What I did instead is went to BTS on-time data that keep track of at least all the states' domestic flights with their like tail number, origin, destination, departure, arrival time, delay, or canceled information. You can get it like over a month. So I grabbed 2025 January. It can be any month, but doesn't matter. It doesn't tell me how many passenger or flight attendants on it, but there's another database called FAA Aircraft Rego, where you can link the tail number to its model, manufacturer, year, and number of seats. So I joined the two tables by tail number and compute the minimum cabin crew needed by 2 plus maximum of 0, and that's a ceiling function that looks a bit cursed. So basically, you assign one flight attendants for every 50 passenger or 50 seats, at least 2, even if it's a tiny plane. Yeah, so that's what I spent half a week on, just looking at different papers for their data set to see any of them are public, and decided to do that. In terms of available cabin crews in a base, I will just generate some numbers of senior, some numbers of general, junior staff. It shouldn't matter as long as I can get some feasible solution. Yeah. Reference.
Okay. Thank you. Now, if you go back, in the constraints, where were the base sizes sort of built into the patterns?
The constraint of this guy? Or
Yeah. The available R is the
available crew of this rank. Of rank R, no, class R.
Okay, but they've sort of taken the base index out. That does seem strange.
They took base index out of everything, and they kind of just only look at one base, and I was really confused.
Yeah. I think they must just be looking at one base.
Okay, then you can't just. I know like the extra crew is penalized, like because it's more expensive, but you can't just grab infinite amount of extra when needed, which doesn't make sense.
Yeah. They probably will have some pool of them, and typically there's this whole, on top of this, there's this whole workforce management thing, which is about making sure you have the right number of flight crew through time, okay, and through holidays and things like that. Okay, so yeah, as I discussed yesterday, there are some opportunities potentially for domain-independent dynamic programming for the delayed column generation. And there's this technique, which Chris is familiar with, of if you're in a situation, so the reason they do this, the reason they solve the MIP off the LP columns is because that generally gives you a pretty good solution anyway. Okay? And they do this funky stuff where when they solve that final MIP, it might generate some over coverage, and because they allow over coverage, and if they have any over coverage, then they sort of generate the columns that drop out the over coverage a bit, so they sometimes you can get, imagine it's a vehicle routing problem, you've got to go everywhere, and you solve that MIP, and there's one place you're going to twice, then the two columns that go there, you can drop that stop out. Okay, so you can generate columns that drop that stop out just from the columns you've got at the moment, and then solve the MIP again, and it'll be a little bit cheaper because you won't have to go there. That's the sort of thing you can do with over coverage. Okay, so there's sort of iteration on over coverage, but then the really funky thing, and this is much trickier, is to, if you have an LP solution and an IP solution and they're close to each other, don't just generate columns with negative reduced cost, allow columns with positive reduced cost as well, so long as it's smaller than that gap, so long as the final positive reduced cost is smaller than the gap. If you can actually generate all those columns, well, if you have the LP optimum and the IP optimum, you can prove that any pairing, any column, whose reduced cost is bigger than that gap, won't be in the integer optimal solution.
Right.
So if you generate all the columns in the gap, and then re-optimize, then you have the optimal solution. And that only works if you get a small LP-IP gap. Okay? But it's a very common technique in enumerating everything in the gap.
So is the IP gap of the bad, like the bad solution which you got, is the gap between the LP and that one?
Well, the IP is when you just switched over around IP.
Okay.
And the thing is, you don't even have to have an IP solution. You can just pretend you've got one. You can say, I think I can solve this to within this much gap. So I'm going to generate all the columns in the gap. Now I'm going to solve the IP. And if the actual optimal solution is smaller than what I estimated as my gap, I'm done. Otherwise, my gap's actually bigger and I actually have some more columns. Okay. Don't laugh. This is a big thing in Lucas in my former postdocs PhD student.
Works really well until you're doing two objectives at once and you guess the wrong objective, and then you have to solve the second objective like 10 times to prove that the first objective's wrong, and then you get to solve it really quickly after that. So
Yeah.
it's good stuff.
So this idea, it's actually one of the areas where, and the reason it works so well is because you avoid branching. Okay, you just do, you sort of solve the root node, and then you generate a few more columns at the root node, and then you solve the IP and you say you have done. Okay, but it's reasonably funny. And any delayed column generation will either have to be written to run fast, it'll have to be written in a compiled language, or use something like domain independent dynamic programming, or CP. The thing is, the column generation problem you can formulate to run in some other language like
Mhm.
CP or domain independent dynamic programming, in some other modern package, and then they're written in compiled languages, so they're fast. So, okay.
Are we allowed to write our stuff in C++?
Yes, you can.
Okay.
Because I'm marking it. Okay. Yeah, I'm capable of marking C++. That's just. And I'm even capable of compiling and running it. So, linking it, doing all those nasty things. Okay. Good. That is good. We'll have break now, up until the top of the hour.